Hello everyone! In this video we will continue to examine topic 1.2 uncertainties and errors and continue to unpack random and systematic errors. Alright, so in the last video we discussed the difference between introducing systematic and random errors. A reminder that systematic error is error that is always in the same direction over multiple measurements, and random error is error that ends up being in different directions over multiple measurements. Notice that systematic and random error is introduced. It's not a thing you do. It's introduced into your measurement due to many different sources of error, which can either be methodological or instrumental. Now, some more vocabulary related to this. It's nice to have a word to describe a measurement that has either sort of low random error or low systematic error, and we use different words to do so. In ordinary English, these words basically mean the same thing. So I'm about to teach you a technical difference between these two words. In ordinary English, they almost always mean the same thing, and even casually in physics, we'll sometimes be a little bit incareful about which word we use. But it's important to note that in sort of formal scientific writing and in your physics lab reports in particular, you want to be very careful about which word you choose. And these two words are the difference between precision and accuracy. And we say that a measurement is precise, very precise, if there is low random error. We say that a measurement is accurate if there is low systematic error, okay? So imagine you take multiple measurements. Usually this is introduced via these targets over here. So I'll start with these targets. And let's say you're trying to hit the real or the true value. In this metaphor, the real or the true value is represented by the target. As a scientist, you don't know where the target is, but let's say for a second that you know where the target is for one moment, and you're trying to hit the target with your measurement. So let's say you take 5 or 6 measurements here. If you get sort of this cluster where you have a lot of measurements tightly clustered around the true value, that is the center of that target, then you would have measurement that is both precise and accurate. Why? There is low random error, that is low spread in these values. Right? These values are only off a little bit in different directions. And there is low systematic error, so they are not off all in the same direction by a particular amount. Now examine this target over here. Now, this is a shooter or whatever we want to say for maybe it's a bow and arrow or a rifle or whatever, but this particular set of measurements will be precise but not accurate. Why? Well, there's still low random error. That is, as you take multiple measurements, those values end up basically in the same spot. They're really close together. But they're all off from the true value in the same direction by roughly the same amount. That deviation from the real or the true value is the systematic error. And so this is a set of measurements that is precise but not accurate. This is the kind of measurements that you'll get if, for example, you're measuring the height of something and you chop off the end of the ruler. If you chop off the end of the ruler, you have what is known as a calibration error. Then you will systematically get the wrong height, and there's nothing you can do about it if you don't know that that error is there. So if you can't see the target, you don't know that anything has gone wrong. Now, if you see the ruler, you can correct for it. And in this case, we could correct for this data as well, right? If we know that that error is there, we simply subtract this, and now we have a very precise and accurate measurement. All right, so what about this case right here? Well, in this case, our data is all kinds of scattered, all right? So much larger spread in the data. And there is significant random error, but notice that random error from that center point, that true value, is in all different directions. And so this would be an example of something that is imprecise. Notice, though, that if you take sort of the average measurement, of these blue x's, it lands directly in the center. That is, if you take these blue x's and average them, you really did measure pretty accurately the value that you were trying to measure. Okay, so this would be an example of imprecise but accurate data. Notice you need to shoot a lot of shots if you're imprecise but accurate. That is, you need a lot of measurements so that the average of those measurements reduces the effect of the random error. Notice it doesn't reduce the random error. If you take more shots, you're still going to hit over here and over here and over here, and so on and so forth. But it reduces the effect of the random error on your actual measurement. Then you could have the disaster case. You could have both significant, systematic, and random error, at which point you would be both imprecise and inaccurate. So if the target is over here and this is the real value and this is your data, well, I guess you just haven't done a very good job, have you? So you have both significant random error and significant systematic error. Notice you can have both, and sometimes you will. Now, these targets are sort of a classic way of representing this, but coming back to sort of that histogram for the beginning, how does that line up with, like, actual measurements rather than just sort of a target? Well, often in some sort of axis, there'll be a true value. This is the value you're trying to measure on that axis, no matter where it is. And you can represent your measurements with this blue curve. So this is a little bit harkening back to this shape. Same kind of thing. You're taking multiple measurements, and there's some true value that you're trying to measure with your multiple measurements. In this top left-hand case, you can see that that bell curve is pretty tight, and so there's not very much spread in the data, and that average is right near the true value. So this would be a precise and accurate measurement. Notice that if you have a precise and inaccurate measurement here, okay, you can see that there is some systematic error here that's sort of moving all of these measured points to the right. And notice, if you didn't know the true value, you can't tell the difference between these two cases. So this is definitely the scary one. And each of your values are moved to the right, and there's low random error. So this is a precise but inaccurate measurement. Notice that in this bottom left-hand corner, if you take enough data to fill out this bell curve, notice you need more data to do so, but now your average value is right on target for the true value. You still have significant random error, but that random error is not affecting your measurement nearly as much, as long as you have enough data to fill out this bell curve. And then, of course, you can have both. Okay, you can have both. Notice something interesting here. Notice that if you are precise but inaccurate, that is to say that if you have low random error but significant systematic error, all right, you will actually measure the true value of the measurement less frequently than if you are imprecise and have systematic error of the same size. So notice that as this bell curve sort of widens out, okay, you notice that you actually do measure the true value more times in this bottom right-hand case than you would in this bottom left-hand case. Another way of saying it is that sort of greater spread in the data actually means that you'll probably hit the center of the target a little more often, even if you have the same amount of systematic error. That's not super important, but it's just a word of caution, of warning, because sometimes we look at sort of the tightly bunched nature of our data and we assume we're totally on target. And as it turns out, sometimes these cases are the very trickiest, the very scariest.